Hello again, AP Physics students. In today's lesson, we're going to talk about what an electric dipole and an electric dipole moment is. And then we're also going to do some calculations, more complicated calculations, dealing with determining the net electric field produced by a couple of source charges and also by the electric dipole. So this is going to be a good place to start in terms of what an electric dipole is. So in the diagram I have below, what I have is I have two charges. So one charge is negative q and one charge is positive q, and they are separated by a distance s. The one thing I want you to note in the diagram is those two charges have the exact same charge magnitude. It's just the signs of the charge are opposite. In terms of defining what an electric dipole would be, so an electric dipole consists of two oppositely charged particles that, one, have the same magnitude. It's going to take the absolute value of negative q and positive q. It would just be q. And they're separated by a really, really small distance. So again, whenever you see that like prefix di, it's meaning two of something. So in this case, we have two oppositely charged particles, same magnitude, opposite charge, separated by a really, really tiny distance. So I can give an example of this. We took like a HCl molecule. We could actually take an HCl molecule, we could break it down into being made up of a positive charge, which would be the H plus ion, and a negative charge, which would be the Cl ion. And the HCl molecule, like the hydrogen ion and the chlorine ion, they'd be separated by a distance, which would actually be a bonding distance of 1 times 10 to the negative 10 meters. Okay, so that's one example of what an electric dipole would be, an HCl molecule. We're going to take this a step further and talk about something called an electric dipole moment, which we're going to use the variable lowercase p to represent. Now, we already use the variable lowercase p to represent momentum back in physics 30. So in this situation, this is not going to represent momentum. It's going to represent something different. I suppose it's just unfortunate that we have one variable that can be used to represent two different things. Now, in terms of what an electric dipole moment is, it's a vector, p, and we define it as a vector that points from the negative to the positive charge in an electric dipole. So once again, I have a picture of my electric dipole at the bottom of the slide. So again, I have my two opposite charges separated by distance s. The charge magnitudes are the same. My electric dipole moment would point from the negative to the positive charge in an electric dipole. So we can actually draw this vector on the picture here. So in this case, the electric dipole moment vector would just point from negative to positive charge, which would be, from our perspective, towards the right side of the page. The magnitude of the electric dipole vector varies directly with the product of the charge magnitude, Q, and the separation between those two charges, which is the magnitude of the electric dipole moment. So what I'm really saying here is I'm just going to give you an equation that can be used to calculate what the electric dipole moment is. So my electric dipole moment varies directly with both the magnitude of the charge of one of the ends of the electric dipole multiplied by the separation between the two. So my magnitude, I just dropped the vector sign in. My magnitude of this dipole moment would be absolute value of Q times S. Now you're probably wondering, like, well, what's the point of this thing? Like, why have we actually defined what this dipole moment is? Well, it's all about what happens if you subject the actual dipole itself to an electric field. So what ends up happening is if you subject a dipole to an electric field, the dipole will rotate about its center of mass. So the center of mass of this dipole would just be directly in the center of where you have those two opposite charges. So if you take that dipole, subject it to an external electric field, it's going to rotate so that the electric dipole moment is going to line up with the direction of the electric field. Okay, so the significance of this vector is just going to tell you like how is this dipole going to rotate if you put it in an external electric field. So let's say, for example, that we suddenly subjected this electric dipole to an electric field that points towards the top of the page. So what would happen here is, so we start off with our electric dipole moment pointing towards the right, and what the electric dipole moment wants to do is it wants to line up with the direction of the external electric field. So if my dipole moment points towards the right, and the electric field is going to be towards the top of the page, then what direction would the dipole as a whole rotate? Well, P needs to line up with E, so it would be rotation in a counterclockwise direction. Okay, so that's a significance of the electric dipole moment. It's going to tell you if you subject the dipole to an electric field, an external electric field, how is the dipole going to line up with it? And the dipole lines up with it so that the electric dipole moment, which always points from the negative to positive charge in an electric dipole, will line up perfectly with that external electric field. So that's a significance. There'll be a bit more of an application of this when we actually get into magnetism and talk about a magnetic dipole moment, but for the time being, we'll just focus on the electric one. Okay, one other thing before we kind of get into some problem solving in looking at how to calculate net electric field, and we did this back in physics 30. I mean, we may have had like a couple of source charges, and we want to figure out the net electric field at some point, either between the source charges or away from them. To do this, we use something called the principle of superposition. And essentially the principle of superposition does is you basically just look at the electric field contribution from each source charge separately, and then you add all the different contributions together. Now, we're going to write it in a bit of a different equation here. So I'm going to write it down in terms of our three-dimensional equation for electric field. So in the equation that I see here, I have the net electric field, which is sigma E, is equal to 1 over 4 pi epsilon naught. Now, just a reminder, this whole part here, the 1 over 4 pi epsilon naught, that is Coulomb's constant. So Coulomb's constant multiplied by the sum from I equals 1 to n. Now, what's the n value go up to? It'd just be the total number of source charges that you have, okay? And then that would be equal to qi over ri squared, where r is going to be the distance from your point of interest to where the actual, sorry, other way around. I think it's the distance from the source charge to our point of interest, although we're doing the magnitudes, the direction doesn't matter. And if we want to express as a three-dimensional vector, we just multiply by the unit vector as well. So just saying, really what it's just saying is if you want the net electric field at a point, then you just need to figure out the contribution of every source charge individually and add them together, which we can write in the summation notation. Now, it turns out that most of our problems are actually not going to be in three-dimensional space. And if problems are not in three-dimensional space, it's actually a lot easier if we do not deal with unit vectors and three-dimensional math. In fact, even two-dimensional scenarios are generally not ideal. So if there's ways in which we can look for convenient symmetry, we can actually even take a two-dimensional scenario and break it into a one-dimensional scenario. If we only have things going on in a straight line, then it becomes significantly easier to deal with because we don't have to worry about vector components, in which we'd need to do in either a two-dimensional or a three-dimensional case. So the second example, I'm going to show you like how we can look for convenient symmetry that's going to make things much, much easier. Yeah, and I said if you can actually do this, if you can find convenient symmetry in a problem and reduce to a one-dimensional scenario, then you do not actually need to calculate unit vectors. In that case, it's actually a lot faster just to calculate magnitude and direction of our net electric field separately, kind of like how we did in Physics 30. So it's really only in the scenario of maybe three-dimensional vectors or three-dimensional space, or maybe some 2D problems, we'd actually have to worry about unit vectors. But again, we're going to try to get away from that by finding ways to turn our problems into one-dimensional problems. Okay, so let's start with this. This is an example of a multiple choice question that you would see on the Physics C exam. So the one thing to note immediately is that you do have 5 possible options as opposed to like the standard 4 that you would have on the regular Physics 30 diploma exam. And this example was taken from the AP Physics C course description. So it was a provided example of a multiple choice question there, but you could very well see a question like this on the exam. Okay, so what do we have? It says we have 2 charges are located on the x-axis of a coordinate system as shown above. Okay, I'm going to label these charges. So I have one charge up here that is positive Q. I'm going to call this one Q1. And then I'm going to call this other one over here Q2. Okay, they're located along the x-axis. That's good. So this is going to be a 1D problem. Now it says the charge, positive 2Q, is located at a distance of positive 3A relative to the origin. So this O right here would just be the origin on the x-axis. And the charge, positive Q, is located at a distance of negative 3A. Now, what we're going to do is we're going to add in a third charge, okay, a third charge Q3. And it says, where should I put a third charge that will result in the electric field, the net electric field at the origin being equal to 0? So what we want here is we want to put a positive test charge, okay, because that's how we figure out the direction of the electric field. Okay, you want to put the positive test charge. Okay, at the origin. And the question, and what I want is I want the net electric field at the origin to be equal to 0. So the question is, where do I need to put a third charge that's actually going to do this? Now, I'm going to solve this question both from a qualitative perspective and a quantitative one. The issue with like the physics multiple choice questions, you don't have a whole lot of time to do these things. So like you do need to sometimes just like try to like qualitatively through logic, just try to like very quickly piece it together and actually use the possible answers to decide like what is actually reasonable here. Okay, but I'll do it in 2 ways. I'll do a qualitative way and I'll also do a quantitative way just to actually like flat out prove like where that charge needs to be located. Okay, so here's how I'm going to do this. So first of all, what I'm going to do is I'm going to look at the origin. Okay, so the origin is where we're trying to figure out where the net electric field is. Okay, so I'll say at the origin. Okay, so we'll say this here is like the location of my positive test charge and it's at the origin. Okay, now what I'm going to do right now is I'm just going to draw some electric field vectors due to both Q1 and Q2. And I'm going to try to draw these vectors in a way that I can actually represent the magnitude a little bit as well. So if we look at our physics 30 equation for electric field, we know electric field, the magnitude is equal to K times the magnitude of my source charge divided by R squared. So the important thing to realize here is there's a direct relationship between the magnitude of the charge and the electric field, and an inverse relationship between R. Now, both Q1 and Q2 are located the same distance away from the origin. Okay, so we don't need to worry about like R in terms of identifying which vector is going to be bigger. So if you look here, okay, so which vector is going to contribute more to the electric field, the origin? Well, first of all, let's identify like what the direction is. Okay, so again, at the origin, the direction of the electric field is the direction a positive test charge would go. So a positive test charge in comparison to Q1 would want to repel away from it. Okay, so we could represent this with a vector that just points towards the right, and we'll call that E1. So E1 just means it's the electric field at the origin due to Q1. And again, it would cause a positive test charge to repel away. Now, E2 would be the electric field at the origin due to charge 2. Now, this is also going to cause a positive test charge to repel away. So E2 is also going to be towards the left. But what I want to do here is I want to show which vector is larger. Now, if we look at the relationship, both Q1 and Q2 are the same distance from the origins. The only thing that's different between the two is the actual magnitude of the charge. So Q2 is bigger than Q1, which means that the electric field due to Q2 is going to be larger. In fact, it would be twice as large. So what I'm going to do is I'm going to draw a vector that's about like twice as large in length here. Okay, and we're going to call that E2. Now, what I'm trying to do in this problem is I'm trying to place a third charge so I can make the electric field here 0. Okay, so look at my two vectors. We want to introduce a third vector that is actually going to make the net electric field 0. So what direction would that third vector need to point? Well, think of this like a tug of war. Like the tug of war is like clearly winning towards the left. So I need to offset it towards the left by putting a vector towards the right. Okay, so we're going to draw a vector that points towards the right. Okay, if a third vector helps out E1, then I can actually balance the electric field at this point here. Now, right away, we can kind of like decide, okay, so where does the third charge need to be? Now, it tells me the third charge is a positive charge. So if I need to have E3 so that it is going to point towards the right, where would you have to put that third charge so it can make the positive test charge repel towards the right? Well, it would have to be towards the left of the origin, okay? Because if charge 3 is towards the left of the origin, then it's going to cause the test charge to repel towards the right. If you had the test charge that was on the right-hand side, if charge 3 was on the right-hand side, then it would cause a test charge to repel towards the left. So that would be wrong. Okay, so immediately we can narrow this down just to two options, okay? Because there's no way the test charge can actually be on the right-hand side of the axis, okay? So I'll just quickly justify this here. I'll say to produce an electric field of 0 at the origin Q3 must be placed to the left of the origin by an unknown distance. We don't know that distance yet. It's either going to be, according to multiple choice questions, negative 6a or negative 2a. Now, we've got to try to figure out which one is it going to be. Is it going to be negative 6a or is it going to be negative 2a? Now again, we can still figure this part out logically in terms of whether it's going to be negative 6a or whether it's going to be negative 2a. Okay, now think about this for a second. So look at the magnitude of this third charge. It's really, 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 really big, okay? So if I put it at negative 2a, for example, so negative 2a would be up here, and it had this charge, the electric field would actually be really, really big. Like it would definitely be bigger than E1, okay? So if again, for example, just go to a different color. So if I actually put the charge, not here, sort of right, we're on this side, on the left-hand side. So we put the charge here, we're gonna compare it to, yeah, we're gonna make a comparison to E1 here. If we put the charge here at negative 2a, then not only would it be closer to the origin, which would make the electric field bigger, it would also have a larger charge, which means that E3 would then be much, much bigger than E1. So that's actually going to offset the tug of war you have there. So that there's no way it can actually be at that distance. So what we really need to do, and I'll justify this in words here. Yeah, this is again like this. If I was doing the AP exam, this is like the logic that would go in my head to like figure this out. So I'd say because Q3 is so large in magnitude, we need to reduce that magnitude. Otherwise, it's going to make the magnitude of the electric field. Otherwise, it's going to make E3 too big. So what we need to do is we need to get this thing further away from the origin. So because Q3 is so large in magnitude, it will need to be further from the origin so that its contribution to the vector E3 is not too large. Therefore, x equals negative 6a seems like a good guess. Again, if we put it at x equals negative 2a, and we look at this equation here, because the charge is big and the distance is small, E would just be too big. Therefore, you'd have the net electric field direction at the origin towards the right. But we can move it further away, then that would make the electric field small enough to offset its larger charge to make it so it's the same magnitude as E3. Okay, so you could, just based on this logic here, immediately identify that it is A. Now, let's say I actually wanted to calculate this, but again, if you're doing this multiple choice question, you do not want to calculate it, okay? You would just simply use this logic and you would do it and you would move on. But again, I do want to show that this does mathematically work as well. Okay, so we're going to do a calculation now. So I want to figure out the net electric field at the origin, and the net electric field at the origin would be the electric field due to charge 1 plus the electric field due to charge 2 plus the electric field due to charge 3. And this is a one-dimensional problem, so let's just establish what I want to be positive. I want right to be the positive direction. Now, I want the net electric field at the origin to be 0, so I'll replace that left-hand side with 0. And then I'm going to take these vectors and I'm going to start to actually account for direction. So if we go back to the previous slide, E1 is a vector that points towards the right. Therefore, I'm going to write down positive E1. E2 is a vector that points towards the left, so I'm going to write that as negative E2. And then I'm pretty sure that E3 points in the same direction as E1, or it must. So that's going to be positive as well. Okay, I'm going to take this equation, I'm just going to manipulate for E3, because E3 is going to contain that unknown distance we're looking for. So this would then be E3 would be equal to, move these two guys over to the other side, and it would be E2 minus E1. Okay, now we're going to plug in our equation for electric field magnitude, which is this equation, and we're going to do it for all three of these electric field contributions. Okay, so E3 would be K multiplied by the magnitude of Q3 divided by, I'm going to say, the distance from the origin to 3, all squared. I guess we don't need to write that as absolute value of the vector. We just write down R03. So again, it's a distance from charge 3 to the origin. This would be equal to K times Q2 over R from 2 to the origin squared, and then minus Q, or K times Q1 divided by the distance from the origin to point 3, and we're going to square that. Okay, we can simplify a little bit at this stage because all the k's would cancel off. Okay, got a k in every single term, get rid of it. And now let's start to replace the variables with the actual values we have in the problem. Okay, so Q3, it tells us, has a charge magnitude. If we go back here, Q3 has a charge magnitude of positive 4Q. So we can just write that down as 4Q. Now, this is the variable we're trying to solve for. We're trying to figure out what's the distance from the origin to where this thing is located. Okay, so we're going to call that variable x. Again, we already established that. Okay, located, Q3 is to the left of the origin by distance x. So we have 4Q over x squared. Okay, this is equal to the magnitude of charge 2 is positive 2Q. So we can just write down 2Q here. And then divide by that distance. 2Q is located 3A towards the right. Okay, so that distance would be 3A squared. And then we subtract Q1, which has a charge magnitude of positive Q, so we can just write it down as Q, divided by, and it's the same distance away, okay, just in the opposite direction, so we can write that as 3A squared. I suppose you could write down negative 3A squared, but you're just going to square it anyways. It's just going to get rid of that. Okay, so again, some things cancel off here. We can get rid of the Q. So the Q's all go away. And then let's expand this a bit. So this would then be 4 over x squared would be equal to 2 over 3a all squared would be 9a squared. Subtract, this would be 1 over 9a squared. Okay, so the right-hand side we can simplify because you have a common denominator. So 2 over 9a squared minus 1 over 9a squared would just be 1 over 9a squared. Okay, let's try to get x by itself. We can do that by cross multiplying here. So what I'm going to do is I'll bring the x up here, and I'll bring the 9a squared up to that side. So that's going to turn it into, well, 4 times 9a squared would be 36a squared. Would be equal to x squared. And if we take the square root of both sides, we then have x is equal to the square root of 36a squared. Square root can be positive or negative. So you have positive or negative 6a. But we're only going to take the negative answer here because we know that it has to be towards the left. So x is going to be negative 6a because b slash c q3 is to the left of O. Okay, so that's a quantitative justification. Again, multiple choice question, there's no way I'm doing that. Okay, it would just eat up way too much time based on how much time you have to complete the portion of the test. I would do it just by logically piecing it out and kind of just like using the process of elimination with the multiple choice answers. Okay, let's look at something a little bit different now. So let's deal with this electric dipole. Okay, so it says in the diagram shown below, point P is along an axis that is perpendicular to your electric dipole moment. Okay, so if you actually look at the picture here, so again, my electric dipole is aligned in the left-right direction, and I have point P, which is located a distance where if you drew a line to the dipole, it would actually hit this line at a 90-degree angle. Okay, so this point P is perpendicular to the electric dipole. And it says both ends are the same distance away. So it just means it's located directly in the center of this. Okay, it says A, identify the direction of the net electric field at point P. Now, the way we're going to do this is we're going to use superposition. So first of all, let's call this one Q1. And let's call this one Q2. And let's just draw a little triangle here. So I'm just going to draw a line from here all the way up to P, and also a distance from here all the way up to P. And I'm going to call this angle for the time being just angle theta. Now, this is a two-dimensional problem, but like I said, what we want to try to do is see if you can find convenient symmetry to turn this into a one-dimensional problem. Okay, so we want the direction of the net electric field at point P. Okay, so that means put a positive test charge at point P, and let's look at what the electric field would be. I'm going to draw a diagram to the right of this where we're just going to try to figure that out. Okay, so let's say here's point P, and let's draw what the electric field vectors would look like. Okay, so if you put a positive test charge at point P, then in relation to Q1, the positive test charge would actually want to attract to it. So I can draw a vector that would go down and towards the right. Okay, this vector down and towards the right, I'm going to call E1. Okay, so this is going to be the electric field at point P due to the negative side of the electric dipole. Now, in relation to Q2, this positive test charge would want to repel from the positive part of the electric dipole. So E2 would then point up and towards the right. Okay, we'll call that E2. Now, if I wanted to, what I could do here is I could break this into vector components. So I'll do this with a different color. So E2, we could break into having an X component that points towards the left and a vertical component that points up. And we could call the vertical component E2Y. And we can call this horizontal component here E2X. And then here we can do the same thing for this one. So we can draw the vector component of this one that goes towards the left. So we can call this E1x. And a vertical component that goes straight down. So we can call that E1y. Okay, so what I want to do is I want to use symmetrical arguments just to identify what is the direction of the electric field at this point. Well, look at my components diagram. What would the net direction of the electric field be at point P? Well, you should answer towards the left because you can see here the two vertical components actually cancel off. The vertical component of E2 points up, the vertical component of E1 points down, and I'm actually just left with two components that point straight towards the left. Okay, so what I can say here is I can say the y components cancel off, leaving the net electric field. We'll say net electric field at point P, so sigma EP pointing to the left. Okay, so this is actually a good thing. So what we've done is, even though this starts off by being a two-dimensional problem, to figure out the net electric field at point P now, we only have to worry about two components. We only have to worry about the x component of E2 and the x component of E1. Okay, so that's very good news. This is something you should always look for. If you see a two-dimensional problem, see if there's a way to, using symmetrical arguments, reduce it into a one-dimensional problem. Okay, so we know the electric field is towards the left at point P, but now we need to actually calculate what this magnitude is. Okay, so once again, we're going to use the principle of superposition to do this. Okay, so this is part A. Okay, so we're going to go over here to part B. So we want the net electric field at point P. And the net electric field at point P would be equal to the x component due to charge 1 plus the x component due to charge 2. Now, if we look at the diagram, both those components point towards the left, so I'm going to make left positive. Okay, now let's turn this equation into magnitudes. So I think that's what it wants to. It just wants the, it wants the magnitude of the net electric field. Okay, so at point P. So I'll say the magnitude of the net electric field at point P would just be equal to, if left is positive, this would be equal to the magnitude of the x component of electric field due to charge 1 plus the magnitude of the electric field at point P due to charge 2, and only its x component is actually doing anything here. Now, I can further simplify this because these two guys are actually equal. Why are they equal? They're equal because they both have the same charge, magnitude that is. And yes, their charges are opposite in sign, but for the purpose of doing this calculation, the magnitudes are the same. And they're the same distance, Q, and the Q1 and Q2 charges are the same distance from P. And it flat out told us that in the problem. It said P, he's the same distance from each end of the dipole. Okay, so we're going to take this equation. I'm just going to rewrite it. So what I could do here is in the place of E2x, I could just replace it with E1x. Therefore, I could write down the magnitude of the net electric field at point P would be equal to 2 multiplied by the magnitude of the electric field at point 1, and it's x component only. Okay, so that's my overall magnitude is going to be. Okay, let's go back to this diagram now, because what I want to do is I want to write an expression for what E1x is in terms of E1 and the angle theta. Now, it turns out that this angle theta here is actually the same as these two angles of theta. There's an easy way to justify it if you just like extended this and just like looked at just dealt some right angle I don't even call it right angle trig, just knowing that there's 180 degrees in a triangle, you could prove that. I'm not going to show that though, okay? This angle here is equal to those two angles there. Okay, so if I want to write down what the x component is in terms of the angle theta and E1, well, E1x is side adjacent, E1 is side hypotenuse, so we're going to replace it with a cosine ratio. So I can write it then as the net electric field at point P would be equal to 2 times, we're going to take the electric field due to charge 1, and we're going to multiply it by cosine of theta. Okay, now, we need to know what is the distance from Q1 to point P. Okay, so I'm going to draw a little triangle that just illustrates what this would look like. Okay, so let's say we have Q1 is right here, and we'll say point P is up here, and I'm going to draw a little triangle. Okay, where this is angle theta. Now, if we go back to the picture, it tells me that the distance from the center of the dipole up to point P is r. Okay, so my variable r is going to be this. Now, this length here is the distance. Again, if r is the distance from the center of the dipole to point P, and the dipole separation is s, then this distance would just be s divided by 2. And what we want to know is we want to know what this distance is from point P to Q1. So I'm going to call that R1P, distance from Q1 to point P. So to calculate that, that would be R1P would be equal to, use Pythagorean theorem, so this would be R squared plus S over 2 squared. Now, I could expand the S over 2 squared, but I'm just going to leave it in this format here. Okay, now what I'm going to do is I'm going to write an expression for cosine of theta based on the triangle that you see here. Okay, so cosine of theta would be equal to side adjacent over side hypotenuse. Okay, so side adjacent is R1P. Oh, no, wait, it's not. Side adjacent is S over 2. Okay, so this would be S over 2 divided by the hypotenuse, which we just calculated, which is r squared plus s over 2 all squared. Okay, we're going to evaluate this expression up at the top here. So, or not evaluate, we're going to just expand it a bit more. So I'm going to take this expression and I'm going to start to actually do some, I'm going to expand this thing now. So I'm going to take cosine of theta and plug it in here. And we're also going to expand the E1 equation in terms of how you calculate electric field magnitude. So what this would then look like is it would be the net electric field at point P would be equal to, the net electric field at point P would be equal to 2 multiplied by, now E1 would be K times Q1 over the distance from 1 to P, all squared. Okay, so that's what E1 would expand to. And then cosine of theta is S over 2 times, or not times, divided by R squared plus S over 2 squared. Okay, so this part's E1. This part is cosine theta. Now, right away, I can get the 2's to cancel. So this 2 and this 2 right here would cancel off. And then I'm going to take this expression for R1P and I'm going to plug it in right there. Okay, let's see what this looks like now. So this would then be equal to, we'd have K. And by the way, we can replace Q1 with, if we go back to the slide here, it's just going to be the absolute value of Q1 would just be Q. So we're going to turn this one into Q here. Let's just put it in absolute value signs. Okay, so this would then turn into, the numerator would just become K times Q times S. So you'd have K, Q, S is what's left in the numerator, divided by, okay, R1P, we're going to square it, but R1P is the square root of R squared plus S over 2 all squared. And then we're going to multiply by this term of this part over here, which is still part of the cosine theta. Okay, which is going to be, oh, we're going to square this. Yeah, I've got to square R1P squared. And then we're going to multiply by R squared plus S over 2 squared. Now, this part, we have a square root and we're squaring it. So what we can do is we can just write that as KQS over, so we're just going to undo the square root sign then. So I would just turn this one into R squared plus S over 2 squared. And then we're going to multiply by, now square root is the same thing as raising something to the power of 1/2. So we could write this as R squared plus S over 2 squared. And that's the power of 1/2. Now, both these things in the denominator, these expressions essentially have the same base, they just have different exponents. So we can actually combine both the expressions in the bottom just by writing the same base and adding the exponents. So this guy would have an exponent of 1. Therefore, this is where we finally get our answer. So we get the magnitude of the electric field at point P would be equal to K times Q times S all divided by, and it's going to be r squared plus s over 2 squared. And then we combine those exponents. 1 plus 1/2 would be 3 over 2. Okay, so I end up getting I was going to say a relatively nifty equation for the electric field at this point. Okay, but it's still a little bit complicated. Now in part C, we're going to do something to simplify this. Okay, so it says B was determined the magnitude of that field at point P. Now C says rewrite this equation from B if R is, what those arrows mean is it means R is way, way bigger than S. Okay, so let's go to part C. I'm going to rewrite that equation out. So our equation from B was the net electric field at point P is equal to KQS divided by R squared plus S over 2 all squared to the power of 3 over 2. Okay, now here's the deal. If R is way, way bigger than S, what I want to do is I want to look at this, this bottom part here, okay? So if R is much, much bigger than S, then R squared plus S over 2 squared to the 3/2. So if this term is way bigger than S, it actually means that this term is irrelevant because it'd be so small then. So I could say this term yeah, because if S is like R is huge and S is small, then it'd pretty much be going R squared plus some like really, really, really tiny number. So we can actually just ignore this part. Okay, we can assume it's, I don't want to say it's, yeah, I mean, I don't want to say it's approximately equal to 0, but I mean, relatively speaking, compared to R, it's approximately equal to 0. Okay, so what we can do now is in this expression, we can just simply get rid of the S over 2 term. So this would then turn it into the net electric field at point P would be equal to K Q times S divided by, okay, now we're going to get rid of this S over 2 term. So now it would just be R squared raised to the power of 3 over 2. And then things nicely simplify now. So if you look here, this square and that square would actually cancel off. So this would give you the net electric field at point P would then be equal to K QS over R cubed. Okay, and this equation is valid if R is much, much bigger than S. Okay, so what this equation does is this equation allows you to calculate the electric field. So we go back to our previous picture. It allows you to calculate the electric field at point P, which is along an axis perpendicular to your dipole. Okay. Now, for part D, it says, okay, rewrite the equation from C in terms of the magnitude of the electric dipole moment. Okay. So let's take a step back here. So what's my equation for the electric dipole moment? It's P is equal to Q times S. Electric dipole moment is P equals Q times S. So if you look here, I can just do a quick little substitution. I can take P equals Q times S, and I can just replace it in this equation. So then you would get the magnitude of the electric field along an axis that is perpendicular to the electric dipole would be equal to K times P over RQ. So now it's starting to get, it's getting very, very simplified. Or if you wanted to, you could also write it like this. We could also write down Coulomb's constant as 1 over 4 pi epsilon naught P over R cubed. Let's box that. Okay, and that's valid if R is much bigger than S, which typically it should be. Like S is like that, what did I call it? Like the bond distance. So presumably that bond distance, which would be much smaller in comparison to whatever point you're trying to figure out what the net electric field is at. Okay, so that's it for this lesson. You can complete all the problems in the section of assignment 1 called electric dipoles. Now, if you're interested and you want to challenge yourself, so this equation right here was what I did is a big derivation for what the electric field is along an axis that's perpendicular to an electric dipole. If you wanted to, for fun, you could also do this. You could figure out what is the electric field at a point P that is parallel or along the same axis as an electric dipole, and see if you can get the actual expression or the equation. If you go on to D2L for this lesson, I actually included the derivation. So if you wanted to go ahead and like check to see if you can actually get it at the end, you can go ahead and do that. But otherwise, this is optional. It's just simply if you want to try to see if you can get the other equation, if it's along a parallel axis as opposed to a perpendicular one. Okay, and that's it for this lesson, and I'll talk to you later.